In this lesson, we're talking about the composition of functions. Composition is another operation that is represented by this open circle between the two functions f and g. So we can read that as f compose g, but it's equivalent to also saying f of g of x. The order matters, so we'll see what the difference is between f of g and g of f, but we're going to start with this function. F of x is the square root of x, and g of x is x minus 3. So let's find f of g of 7. So f of g of 7 can be rewritten as f of, and then g of 7 inside, and that helps us see that g of 7 is going into f. So we first want to figure out what is g of 7. In my g of x function, we're going to plug in 7, so I end up with 7 minus 3, and g of 7 equals 4. Then we're going to take that and put it inside of f. So f of g of 7 means we're putting 4 into f. Our f of x function would be the square root of x, in this case the square root of 4. So f of g of 7 ends up being 2. We have another one that says g of f this time, so the order has changed, which means now f will be our input function. So g of f of 9 is equivalent to saying g of f of 9. Let's start there, finding f of 9. F of 9 would be the square root of 9, which is just 3. If I take that and plug it into g, we would have g of something is x minus 3, but that x is going to be replaced with whatever f of 9 was. So in that case, it's 3, which ends up being 0. We can rewrite that as g of f of 9 equals 0. The third one there says let's find g of f of negative 4. So we're taking the g function and putting f of negative 4 inside of it. So we want to start with f of negative 4. My f of x function is the square root of x. This ends up being the square root of negative 4, which doesn't exist. This is a non-real number. I can't plug negative 4 into the square root of x because it's not in the domain. The domain of square root of x was 0 to infinity. Negative 4 is not in that domain. So we would just write g of f of negative 4 doesn't exist. In part B, it just says find the functions f of g and g of f. That's different than finding the actual evaluation, because we're finding the function f of g of x, and it doesn't have that on there, but that's what it's implying. That would mean you start with your f function, and inside of f is going your g of x. Our f function was the square root of x, so I'm going to put g of x inside of that, which is x minus 3. There's nothing I can do to simplify the square root of x minus 3, so we could just say that is f of g. But we also want to consider the domain of that composition. Since g of x is our input, that will bring in its domain. Looking at that function g of x, it's the x minus 3. So it's a linear function with no domain issues. Its domain is negative infinity to infinity. But once we have put it into f, we have created this new function, the square root of x minus 3. So now we do have domain issues. Since we're taking the square root, the inside of a square root has to be greater than or equal to 0. We have x minus 3. So x has to be greater than or equal to 3. That is the new domain of f of g. We just write that out as d with a subscript f of g. And bracket 3 to infinity. You're going to write these in interval notation, like always. Let's consider how that compares to g of f. G of f would mean that you start with your g function and you're plugging in f of x. G of x is just x minus 3. But my f function is the square root of x. So we replaced our x with f of x. That happened to be the square root of x. There's nothing I can do to simplify that either, the square root of x minus 3. I don't need those parentheses there. I often write them just to show that we are inputting something into the function, but you could write it just the square root of x minus 3. When we think about this domain, f of x is bringing its domain into that composition, and it does have a limited domain. The square root of x function, I know I can't square it in negative, so it only existed as 0 to infinity. Once I put it into the composition, I didn't create new issues. There's not a change to that square root, and I don't have any fractions or anything that make it irrational. So looking at this, the domain of g of f is still 0 to infinity. What we're considering is what was the input domain, and then once we've put it in, what does that do to the composed function's domain? So it does change the composed function, and that might impact what the actual domain is. So we have a generic question here. How would you define, or how would you find the domain of any function composition like p of m of x? And this p of m of x means that m is going inside of p. So we would first find the domain of the input function. Which in this case is m of x. Then we're going to find the domain of the composition. We hold on to these same domain restrictions that we've been talking about. So if you see square roots or even any even index radical, those are all going to have domain issues. But also rational expressions where you have x in the denominator, those create domain issues as well. On the next page, you have several examples. We're going to use these four functions at the top. We've got f of x, g of x, h of x, and j of x. All right, so the first one's f of g. F of g of x would be equivalent to if I had written it with g going into our f. So I'm going to start with my f function, which is 4x minus 2. 4x minus 2, but the x is being replaced with whatever g of x is. In our case, that's 3 minus 2x squared. Looking at this, we have this distributive property to simplify. And then we can combine like terms. Oftentimes people get confused when they leave nothing on the left side, so I recommend that we keep bringing down the f of g of x so that we show this is the composed function we're trying to finish and calculate. but we also want to think about its domain. So we're going to find the domain of f of g. To find the domain, we need to consider what was our input function's domain. The input function was g of x. Since it's quadratic, it did not have any restrictions. It's negative infinity to infinity. And then we look across, once we input that into the composition, did we create additional domain issues, which we did not. So this domain is still negative infinity to infinity. If we change the order, g of f, means we're starting with the g function, 3 minus 2x squared, but the x is being replaced this time with f of x, which was 4x minus 2. And we need to simplify this. As we're simplifying, we cannot distribute this 2 right now because we have this exponent. Exponents come before multiplication. So we need to simplify what is 4x minus 2 squared first. So I'm going to write that as 3 minus 2 times this 4x minus 2 twice. Since being squared means multiplying by yourself twice. And we can distribute this out. As you get better at multiplying and distributing these binomials, hopefully you'll be able to get this to 16x squared and then see that you're going to have negative 8x, another negative 8x, so that's negative 16x, negative 2 and negative 2 makes that positive 4. We distribute the negative 2 now to get negative 32x squared there, and positive 32x and negative 8, which can combine with that 3, so we end up finalizing this as negative 32x squared plus 32x, and then minus 5. I don't have anything on the left side because I haven't been bringing down the g of f of x. And that's just good practice to help us understand things. But the issue that I see often is people will get confused with why they have nothing on the left side. So they just put a 0 there and they create an equation that didn't exist to actually solve. So we just want to make sure we're bringing down the actual function notation we're using. And then we want to find the domain g of f. So our input function was f. It's a linear function that had no issues to it. So it was already negative infinity to infinity. And then we look across, once it's input to the function, did we create new domain issues, which in this one, we still did not. All right, g of j, I'm gonna write that down here so I have more room. Means I'm starting with our g function and we're putting in j of x. Well, our g function is 3 minus 2x squared. That x is being replaced, and our j of x is the square root of x minus 5. So as we simplify this, we're going to see that we're squaring a square root. Well, squaring that's the inverse operation, leaves me with just x minus 5. So that we can distribute our 2 and simplify that to negative 2x plus 13. G of j of x ends up just negative 2x plus 13. If we only look at the final function, that looks like there were no domain issues the entire time. But we have to remember that the domain of j brings its own domain into that composition. And this is going to be a domain of 5 to infinity. Looking across, we didn't create new domain issues, but we do have that domain from j coming in. So the domain of g of j is 5 to infinity. We also have f of h next. So f of h of x would be equivalent to rewriting this with f and then h of x inside of it. Our f of x function was 4x minus 2. So when I plug in h, I'm plugging in 1 over x minus 2. To simplify that, that would be 4 times 1, since that's the same fraction as 4 over 1. We'd multiply straight across 4 times 1 and 1 times x minus 2, which gives us the fraction 4 over x minus 2, and then minus 2 on the outside. This composition we can leave as 4 over x minus 2 minus 2, but we still want to think about the domain. The domain of h is being brought into that composition, and it has its own domain issue because it is a rational expression. So x cannot be 2. Its domain was negative infinity up to 2, union 2 to infinity. Since the denominator can't be 0, x can't be 2. And I look across that composition, it didn't create a different denominator. So the denominator stayed x minus 2. So it keeps that same domain. Negative infinity up to 2, union 2 to infinity. The last one of these, we're doing h of g. So our h function is putting g inside of it. Our h is 1 over x minus 2, but the x has been replaced. So it's now 3 minus 2x squared. As we look at this one, that whole denominator changes. So I'm not just thinking about h because that's not the input function. Our input function was g, so we need to consider the domain of g, but it's negative infinity to infinity. Then we'll look at the entire composition. So I'm going to simplify this denominator. That'd be 1 over 3 minus 2x squared minus 2, which is 1 over negative 2x squared plus 1, if you want to write it like that. I can't simplify that any further, so we have just h of g of x is 1 over 2x squared plus 1. But if we think about that denominator, since the whole denominator changed, we know it cannot equal 0. Our denominator is negative 2x squared plus 1. And we're going to solve that equation. I can subtract the 1 and divide by negative 2. So x squared cannot equal 1/2. And then we square root both sides. Because we are square rooting both sides, we need the positive or negative square root of 1/2. And that's not going to be a pretty number, and that's okay. It doesn't have to be a pretty number. But what it tells us is that we originally had a domain of negative infinity to infinity until we put this in the denominator, and now negative square root of 1/2 is somewhere on that number line, and we're going to remove it. Positive square root of 1/2, we're going to remove. But every other number is okay. It just cannot be those two values. And they don't have to be pretty numbers. We still can find the domain even without it. So we would rewrite this domain h of g as negative infinity up to negative square root of 1/2 union negative square root 1/2 to positive square root 1/2 union, and then square root 1/2 to infinity. All right, part 2 will go through some graphical explanations of it and the decomposition.